Hello everyone, my name is Yarong Jia. I come from Qinghai Normal University. The title of my report is The Energy of Trees with Diameter 5 Under Given Conditions. The co-authors are Huo Bofeng and Du Qinsong. The report is divided into 5 parts. The first part is Introduction and Problem. In 1970s, Goodman defined the graph energy as the sum of the absolute values of all eigenvalues of its adjacency matrix. The study of graphs with extreme energy has attracted wide attention of mathematicians. On the extreme energy of trees, the maximal, the second maximal, the third maximal, the first maximal energy trees are determined. Argentina made a major breakthrough in this area, determining the first 3n minus 84 maximum energy trees for odd and the 3n minus 87 maximum energy trees for even n. For extreme energy trees with given diameter, there are a lot of results. As for maximal energy trees with short diameter, O determine the structures of the maximal energy trees with center degree of T and diameter 4. Later, G determine maximal energy trees with diameter 4 and diameter 3. Chao and Huo determine extreme energy of a class of tree with diameter 5. Some results have been obtained for the structures of trees with maximal energy of diameter 5, but there are still a lot of difficulties to get the complete solution. We obtained some progress that is the necessary condition to solve the problem. The second part is preliminaries. We first give the characteristic polynomial of a graph and the integral formula. In 1978, for general graphs, Goodman defines graph energy as E_g equal to sum g from g equal to 1 to n, absolute values of lambda g. Demo 1 is recursive formula for characteristic polynomials. Let uv be an h of g, then phi g equal to phi g minus uv minus phi g minus u minus v minus 2 sum c belong to flower c phi g minus c, where flower c is a set of cycles containing uv. In particular, if uv is a pendant h with pendant vertex v, then phi g equal to x phi g minus v minus phi g minus u minus v. In 1986, Goodman and Zhang introduced the definition of the quasi-order of an order acyclic graphs. Let G1 and G2 are an order acyclic graphs, then G1 quasi-order is greater than or equal to G2 if and only if mg1k greater than or equal to mg2k. In order to solve our problem, we introduction some motivations. Chao and Huo first define a class of trees flower T. See the figure 1. On the left, from P1 to PS. On the right side, from Q1 to QT, and we have P1 plus P2 plus PS equal to A. Q1 plus Q2 plus QT equal to B. And they define flower T and ASBT equal to flower T. There is unique graph T and PS1 as QT1T, which has greater quasi-order than other graphs in flower T. Let's say lemma 2. Lemma 2, let P and Q greater than or equal to 1. S and T greater than or equal to 1. S1 and T1 greater than 0. We have T quasi-order is less than Tn plus 1 SQT1T for any T belong to flower T. Let's say finger 2. On the left side, add P to P minus 1 equal to A. On the right side, add Q to Q minus 1 equal to B. If N, S, and T are determined, so is A plus B. If A and B are determined respectively, so are PS1, QT1. Therefore, Tn plus 1 SQT1T can be denoted as TNASBT. Let flower T prime equal to flower T prime NST equal to TNASBT satisfy this condition. It is clear that the tree with diameter 5 and maximal energy should be in flower T prime. For the trees in flower T prime, Jian will obtain some results. See lemma 3. Lemma 3, let Tn plus 1 QT1T equal to G and P greater than or equal to Q plus 2. We have four situations. Then lemma 3 implies that for Tn plus 1 SQT1T equal TNASBT, if P greater than or equal to Q plus 2, then Tn A minus 1 S B plus 1 T. Quasi order is greater than TNASBT. The first part is our results. We narrow down the scope of the subset of trees with maximal energy in flower T prime. We find trees with greater quasi-order in some graph class should satisfy the following conditions. For two non-center vertices that are adjacent to the same center, the difference of the numbers of their neighbors that are patent vertices is not more than 1. Let's say finger 2. On the left side, P and P, their difference is 0. P and P plus P minus 1, their difference is 1. On the right side, P minus 1 and P minus 1, their difference is 0. P minus 1 and P minus 2, their difference is 1. Then, for two non-center vertices that are respectively adjacent to the different centers, the difference of the numbers of their neighbors that are patent vertices is no more than 2. On the left side, we say P. On the right side, we say P minus 1. Their difference is 1. P and P minus 2, their difference is 2. So they are no more than 2. Let's say theorem 1. Let G, this is our results. Let G equal to T plus 1 P minus 1 T1T. T greater than T1, greater than or equal to 1, S greater than or equal to S1, greater than or equal to T1, P greater than or equal to 3. We have two situations. On the one situation, it means take vertex on a P on the left and place it to P21 on the right. Then G1 quasi-order is less than G2. The second situation is the same reason. This is a picture. Theorem 2. Let J equal to T2 S1 S1 T1T. T greater than T1, greater than or equal to 1, S greater than or equal to S1, greater than or equal to 1. We have two situations. Theorem 2 finds the maximal energy trees in a smaller range than Theorem 1. The specific method is similar to the theorem 1. We used lemma 1 and the method of quasi-order obtain the results of theorem 1 and theorem 2. Thank you for your attention.